In this video, we are going to see how it is possible to reduce a network towards a scale-free structure and why is it interesting. We are going to start from the beginning. This is a network, also called a graph. You have certainly already seen such a figure, as it is used in a lot of different domains and it is often used as a symbol of science. This object can represent any system based on interaction between entities. These entities are represented by the nodes, and the interactions are represented by the edges. We present here some examples of systems that can be represented by a network. First of all, the social interactions. In this case, the nodes represent persons, and edges can represent any interaction between them. Friendship, for example, or professional relations. In a communication network, nodes can represent computers, servers, or data centers, and the edges represent an exchange of information between them. We also find network in biology. For example, here the nodes represent neurons and the edges represent synapses. Finally, here is the traffic network of a city. Nodes represent places, and the edges represent roads connecting them. In this last example, it seems useful to precise in which way the roads are going. In this case, we add an arrow on each edge to precise its direction. It is then called a directed network. As we have seen, a network is a single mathematical object used to represent plenty of different systems. It is a good illustration of what Henri Poincaré said. Mathematics is the art of giving the same name to different things. Let's now introduce a particular type of network, the so-called scale-free network. This is an example of a scale-free network. It is a network in which most of nodes have few connections, but some nodes have a large number of connections. We call these later nodes the hubs. Here, we note for each node the number of connections that it has. This number is called the degree of the node. If we report for each degree the number of nodes having this degree, we obtain this type of distribution, called a power law. We give then the following definition. A scale-free network is a network whose degree distribution is a power law. On the other hand, let's consider an homogeneous network with no hub. As previously, we report the degree for each node. Now, the distribution obtained is a Poisson law. These are two families of networks which are often encountered in real systems. Indeed, we are going to see via few examples that the scale-free property appears naturally in a lot of networks. The first example of this type of network has been highlighted by Derek Price in 1865, when he investigates the network of scientific collaboration. In this network, the nodes represent scientists, while edges correspond to a collaboration between them. It appears that some major scientists have a large number of connections, while most of them have few connections. In this work, the term scale-free was not used yet. In 1999, Albert Laszlo Barabasi and Reka Albert studied the structure of the budding World Wide Web, and the same structure appeared. A majority of websites with few connections, and some websites with a very large number of connections. Within this article, the term scale-free has been proposed. This work has really launched the study of scale-free networks. Since then, a lot of interconnected systems have been proven to be scale-free networks. For example, the network of the interconnection between airports. Or again, the network of sexual partners, as shown by Lily Rose in 2001. One can wonder why so many networks endorse this scale-free structure. It is due to the mechanism of preferential attachment. In this process, appearing in many different contexts, the more an entity is connected, the more it attracts connection. You can notice that this mechanism is implied in the emergence of the networks in the previous examples. This mechanism is known for a long time and has been called with different names. We find, for example, the rich get richer effect, the cumulative advantage, or the Mathieu effect. We are going to see now some particular properties of scale-free networks. And first, the robustness to failure. Let's consider the scale-free network. It can be, for example, a communication network or an airport network. Now imagine that a random failure affects two nodes of the network. For example, it can be a computer who crashed or an incident in an airport. As these failures are random, there is a high probability that the nodes affected are small nodes. The networks obtained after removing these nodes remains well connected. This is why scale-free networks are said to be robust to failure. At the opposite, let's imagine that there is some attacks targeted on the hub. In this case, the network will be completely disconnected, preventing the communication between some nodes. This is why scale-free networks are said to be vulnerable to attacks. However, this feature can be used as an advantage. Let's consider the case of a social network. We study the spreading of an epidemic over this network. At each step, an affected individual will infect its neighbor with a certain probability. We can see that once the infection has reached the hubs, the epidemic affects quickly a large proportion of the population. However, a good strategy would be to identify the hubs at the beginning of the epidemic and vaccinate them, just that the epidemic cannot spread through them. It appears then that the epidemic can't reach a lot of individuals. Vaccinating the hubs is then a good solution to protect the population. However, in practice, the identification of the hubs is too complex to use this strategy. A last example of remarkable property of scale-free network is about network navigation. Network navigation is a problem of going from a starting point to a destination point just by knowing the position of the neighbors of the current node and the position of the destination. In 2009, Bogunia and Krikov showed that it's possible in a scale-free network to design a method giving a road really close to the best road. These are some of the most known properties of scale-free networks, but there is other ones, and some are still discussed. Given the feature endowed by scale-free network, the question that we pose is the following. Is it possible to modify an arbitrary network into a scale-free network? Our idea is as follows. Considering an initial arbitrary network, we want to find a partition of this network such that the network resulting of this partition is a scale-free network. This idea could work. But does it have any sense to reduce a network like that? Don't we lose all the information contained in the initial network? In order to give meaning to this reduction, we want the new network to be similar in a certain way to the initial network. We break down this similarity into two aspects. We want to preserve properties of the initial network, and we want the two networks to be as close as possible. These two objectives raise two questions. Which properties do we want to preserve, and what does close mean for two networks with different number of nodes? Before answering these questions, we are going to see in detail which network we consider. The networks that we consider are directed networks. As we have seen, it means that we assign a direction to every edges. The network has to be strongly connected. It means that it exists a path going from any node to any node in the network, as in these examples. The network has to be weighted, which means that we assign a real value to every edge. In general, this value corresponds to a flux from a node to another. Finally, the network is a flow network. For every node in the network, the sum of the weights coming in is equal to the sum of the weights coming out. For this node, we have 2 plus 3 coming in equals to 4 plus 1 coming out. Here we have 3 equals 3, and finally 3 plus 1 equals 4. Then, the initial network that we are going to reduce respects these 4 properties, and we want that the reduction preserve these properties. It appears clearly that by partitioning the network, we naturally preserve the 3 first properties. In the following, we are going to focus only on how to ensure the final network to be a flow network. The other aspect we are focusing in is the network closeness. Before defining this notion of closeness, we introduce via an example what is known as a random walker. Consider this network. One can verify that the properties introduced before are respected. Now consider that a random walker is placed on a node. In this first step, there is only one edge available, hence he follows it. At the second step, 2 edges are available in front of him. To make his choice, it will randomly choose the edge in function of the proportion represented by the weight of the edge with respect to the sum of all weights. By this way, the random walker will go straight forward with a probability of 40% and it will turn right with a probability of 60%. At this step, the probability to take each of the edges is 50%, and so on. Rather than doing it manually, we are going to make a simulation, and we will count how many times the random walker passed by each of the nodes. On each node, we display the number of passages, and below, the percentage that it represents. We constate that the percentage tends to stabilize the random value. This value does not depend on the starting point of the random walker. It is proven that the percentage always converges if the network is strongly connected, which is always the case in the network that we consider. These values are known as the eigenvector centrality of the network, and there is some direct way to compute it. But the example of the random walker gives a good intuition that this value measures the relative importance of each node within the network. Thus, we will want that our final network to have an eigenvector centrality close to the eigenvector centrality of the initial network. However, the two networks do not have the same size. We are going to see now how to compare the two eigenvector centralities. Let's consider an initial network and a partition of it. This partition produces a new network. This network is also weighted, but as we don't know yet how to compute its weight, we denote them A, B, C, D, and E. Now that we have two networks weighted and strongly connected, we can compute their eigenvector centrality. We will say that the networks are close together if their eigenvector centralities are close together, which is if X is close of the sum in the blue zone, if Y is close to the sum in the pink zone, and so on. The error between the networks is then the sum of the squared error in each part. Giving this definition, is it possible to choose the weights such that the network is a flow network and the eigenvector centralities are close? The answer is yes, in some cases at least, as we are going to see now. We introduce what we call a merging. It is a particular partition, where only two nodes are merged together, as you can see in this example. In the case of a merging, we have shown that it's possible to find the new weights such that the finite network is a flow network, and the error is equal to 0. This result can be viewed as follows. Imagine a random walker on the initial network. The proportion of time that you will spend on each node is denoted by the letter from A to I. If we consider a network resulting of a merging, we know how to compute its weights such that the random walker will spend the exact same time in each zone. Additionally, the weights can be chosen to ensure the final network to also be a flow network. Now that we know how to compute the weights in the case of a merging, we are going to see how we can use this result to build an algorithm to create a full partition of the network. Consider an initial network. Consider this first edge in red. We compute the network obtained after merging this edge. We repeat this operation for the second edge, and so on, for all edges. Then, among all this network, we choose the one which is the most scale-free. We compute the weights of the new network according to the result that we have seen previously. Then, we restart by considering this new network. We stop the algorithm when the network obtained is small enough and or scale-free enough. Let's remark that if the initial network is really large, it will be computationally too demanding to test every edges. Instead, we test only a random subset of edges. We have shown numerically that this choice has no major impact on the efficiency of the algorithm as soon as the subset contains a tenth of edges. We are going to observe now the result of this algorithm step by step on a very large network. This is the city of Grenoble, in France. We are going to apply the algorithm to the urban traffic network of the city. On this simulation, we can see numerous informations. On top left, we see the initial network, and the current partition will appear over it. The color bar indicates the number of nodes that contain each zone. On top right, we see the current network resulting of the partition. On the bottom, we can see three different curves plotted in log-log representation. The dotted black line is the degree distribution of the initial network. The blue line is the current distribution. The dotted red line is the scale-free target distribution, which is the perfect power law that we would want to reach. In this simulation, we test at each step 20 edges. We define here a node as a node with at least 15 connections. In the current network, we can see the emergence of hubs, represented by diamonds. We can observe that the algorithm drives the network really close to the desired distribution. Thank you for watching this video. This work has been made for my PhD thesis in the next team of GIPSA-lab in Grenoble within the ERC Scale-free-back project. You can find in the description some references about this work and some links to have more information on our project, our team, or our lab. Thank you.